In this section, we're going to jump around and do a little bit of material from number theory. Let me start with a divisor. So this is a definition. A natural number m is a divisor of n if n divided by m has no remainder. If m does not equal n, then m is called a proper divisor. So really quickly, 5 is a divisor of 20 because 20 divided by 5 equals 4, has no remainder. As an example, let's compute all the divisors for 32. Now in this problem, I'm not asking you for all the prime factors or anything like that. I'm asking you for all the possible factors. So the way we do this is the first thing we do is pull out our calculator, and I'm going to take the square root of 32 like I do all the rest of the problems. So I see the square root of 32 is 5 point something. So what I do is I say the square root of 32 is approximately 5. So I don't want just the prime divisors, I want all possible divisors. So what I do is I make up my list of numbers 1, 2, 3, 4, 5. So notice I'm not just using the prime numbers, I'm using all the numbers up to 5. And then I look to see how much each of them goes into 32. So if you look at the number 1, 1 goes into 32 32 times evenly. 2 goes into 32 16 times evenly. 3 does not go into 32, but 4 does, 8 times. 5 does not go into 32. So what we do to list all of our factors is I look at this list and I go down this column and then up this column, and it lists them all in order. So for my divisors, we have 1, 2, 4, 8, 16, and 32. And the way that I read them, I read down that side and up that side. Now we're also going to want to know all the proper divisors, and that's not hard. Once you have the divisors, you have all the proper divisors. All you have to do is leave out 32 itself. So it's really the same as all the divisors, except you just take away the number itself. Compute all the divisors for 144. Well, you probably remember that the square root of 144 is equal to 12 exactly. So I'm going to write up all my numbers up till 12. There they are. I'll do this one real quick. 12 times 12 was the one that we just did with the square root. The 1 is always easy. 1 times 144. You may need to use a calculator to help you out with this part, but I know most of them off the top of my head. 2 times 72, that also equals 144. And you can see every time I do this, every product here is equal to 144. So now how many times does 3 go into 144? Well, I happen to know that it's 3 times 48, 4 times 36, Now the last digit of 144 is not a 5 or a 0, so I know that 5 does not go into it. Now, since 2 goes into 144 and 3 goes into 144, I am guaranteed that 6 goes into 144. In fact, it's 6 times 24. 7. Does 7 go into 144? Well, the only way to know for sure is to do the division. 144 divided by 7. Since there's a decimal, there would be a remainder if I divided by it, so I'm going to cancel that. Now let's take a look at 8. 8 shouldn't be too bad. If you look, 4 times 36 was 144. That means that 8 times 18 is 144. Does 9 go into it? Well, let's count the digits. 1 plus 4 equals 9. That means 9 goes into 144. How many times? Well, I believe it's 16. 10 does not go into 144. And if you try 11, 144 divided by 11, that's got a decimal, so we know that it does not evenly go into it. So what we have left over is the complete list of factors, not just the prime factors, but all the factors. So if you go down and then up, you can read them all. Let's take a look at my list of divisors. So what I'm going to do is go down here, 1, 2, 3, 4. Let me go ahead and collect those. I have 6, 8, 9, and 12. Now you don't list 12 twice. So then as I go up the other column, I have 16, 18, 24, 36, 72, and 144. If I just want the proper divisors, it's the same list, except we're going to drop 144. So 1, 2, 3, 4, 6, 8, 9, 12, 16, 18, 24, 36, and then 72. Compute all the divisors of 28. So we take the square root of 28. Let's see what that ends up being. A little more than 5. So this is approximately equal to 5. So I only need to do 1, 2, 3, 4, and 5. This one I'm probably going to be able to do in my head. Starting with 1, well, that's always the easiest one. 1 times 28, 2 times 14. 3 doesn't go into it, but 4 does, and neither does 5. So my divisor list is very short. We have 1, 2, 4, 7, 14, and 28. And then the proper ones, same list, 1, 2, 4, 7, and 14. I just don't include 28. Now, one of the things that occurred to the people who were hunting for primes and some other things is, check this out. If I take a look at the number 28, it equals 1 plus 2 plus 4 plus 7 plus 14. That is, it's the sum of its proper divisors. Count. 1 plus 2 is 3, plus 4 is 7, plus 7 is 14, plus 14 is 28. These all of a sudden became really interesting numbers because it was found out that not all numbers are like this. There's only a few, for example. Here, 6 equals 1 plus 2 plus 3, and 1, 2, and 3 are the proper divisors of 6. So what we do is 28 and 6 are known as perfect numbers. So let me go ahead and define that. A perfect number is a natural number that is the sum of its proper divisors. Not all the divisors, just the proper divisors. Most numbers are not perfect. The next two perfect numbers are 496 and 8,128. Show that 496 is perfect. So I need to show that it's the sum of its proper divisors, so we need to find its proper divisors. So just like we did before, let me go ahead and get its square root. I get 22 point something. That means I need to make up a list of numbers that goes from 1 up to 22. And then I'll go ahead and start doing my multiplications. 1 times 496, that's easy. As I go through here, I'm going to make heavy use of the calculator throughout the whole problem. 2, well, let's take a look. 496 divided by 2, that's 248. Does 3 go into it? Let's see. 4 plus 9 is 13, plus 6 more is 19. 3 doesn't go into it. So this is very important. You should know this. Since 3 doesn't go into the number, no multiple of 3 goes into it either. That means once I know that 3 doesn't go into it, 6 won't, 9, 12, 15, 18, 21. None of those will work because they're all multiples of 3. Now let's go ahead and try 4. 496 divided by 4 gives us 124. We know that 5 does not go into 496 since the number does not end in a 5 or a 0. Since 5 doesn't go into it, neither does 10, nor 15, which I already canceled, nor does 20. Now let's take a look at 7. Decimal. 7 does not go into the number. That means that 14 won't go into the number either, and neither will 21, but we've already canceled that one. Let's check 8. I happen to know that 8's going to work, but let's find out what the other factor is. 62. 11. We don't specifically have a test for 11, so using the calculator will work for me. 496 divided by 11. Decimal, so 11 will not go into it. Since 11 doesn't work, neither will 22. Moving on to 13. 496 divided by 13. 13 does not go into it. Let's try 16 while I'm here. it goes into there 31 times. So let me take out the 13. It didn't work. 16 times 31 times. And then all I need to check is 17 and 19 yet. $17 does not work. Let me go ahead and try 19. Neither does 19. So I can get rid of the 17 and the 19. So let's take a look then at my proper divisors. So I want 496 to be the sum of its proper divisors. So once again, I'll count down the columns this way and then count up this way as I go. So as I go down the column, I got 1, 2, 4. Here's my list. 1, 2, 4, 8, and 16. So 1, 2, 4, 8, and 16. And now if I reverse my direction, I've got 31, 62, 124, 248, and stop there. Remember, we're talking about proper divisors, so I'm not talking about all of the ones. Now let's see if 496 is the sum of those. So is 496 equal to 1 plus 2 plus 4 plus 8 plus 16 plus 31 plus 62 plus 124 plus 248. Well, you know that I know that it does, but I'm going to just show you. 1 plus 2 is 3, plus 4 is 7, plus 8 is 15, plus 16 is 31, plus 31 is 62, plus 62 is 124, plus 124 is 248, plus 248 gives us our 496. When we did the proper divisors of 32, I had the following. So we had 1, 2, 4, 8, and 16. Now, if I add them together, 1 plus 2 plus 4 plus 8 plus 16, what do I end up getting? 1 plus 2 is 3, plus 4 is 7, plus 8 is 15, plus 16 is 31. 31. Notice that 31 is less than 32. 32 is called a deficient number. The proper divisors of 144 are 1, 2, 3, 4, 6, 8, 9, 12, 16, 18, 24, 36, 48, 72. Now if I add all of those up, 1 plus 2 plus 3 plus 4, well, you get the idea, I think. Let's see how much this all adds up to be. 1 plus 2 is 3, plus 3 is 6, 10, 16, 24, 33, 45, 61, 79, 103, 139, 187, 259. Now in this case we have 259 is greater than the original number. So 144 is called an abundant number. The way I think of these is the following. We're going to be deficient if you just don't have enough proper divisors to add up to the number itself. And it's abundant if the proper divisors add up to something more than the original number. So it's got too many divisors in some sense. You can think of the perfect ones as being the Goldilocks kind, just right. So let me write the definitions of these things. A deficient number is a natural number that is larger than the sum of its proper divisors. An abundant number is a natural number that is less than the sum of its proper divisors. So as an example, determine if 60 is deficient or abundant. Well, as usual, let's take the square root to begin. I get 7 point something, so the square root of 60. So I need to include 1, 2, 3, 4, 5, 6, and 7. Most of these are pretty easy for me to do without the calculator. And then 7 does not go into 60. So it has a lot of divisors for how small it is. Well, let's go ahead and add up the proper divisors. So my proper divisors, we have 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. Just seeing as we have so many proper divisors here, and the number is being as small as it is, I'm guessing this is going to end up being an abundant number. So let's go ahead and see what happens. I have 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 10 plus 12 plus 15 plus 20 plus 30. Well, let's add them up. 1 plus 2 is 3, plus 3 is 6, 10, 15, 21, 31, 43, 58, 78, 108. And that is greater than 60. So 60 is abundant. Determine if 75 is deficient or abundant. So let's go ahead and get the square root of 75. I believe it's going to be 8 point something. Yeah, it's 8 point something, so all I'll do is go up to 8. We have 1, 2, 3, 4, 5, 6, 7, 8. 1 times 75. No even number is going to go into 75, so I can take out all the even ones right off the bat. 3 goes into it 25 times, 5 goes into it 15 times, and 7 does not go into it. So my proper divisors, what do we have? We have 1, 3, 5, 15, 25, and that's it. So then let's check out and see what they add up to be. 1 plus 3 plus 5 plus 15 plus 25. What's that equal? So we have 4 plus 5 is 9, 24, 49. 49 is less than the original number of 75. So 75 is deficient. Next, we have amicable numbers. I guess the best way to do this introduction to these kind of numbers is by way of an example. So let's start with the square root of 220 and see what we get roughly. $14 point something. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, 1 times 220 is easy. 2 times 110 is easy. Now for the 3, 2 plus 2 plus 0 is 4, and 3 does not go into 4. So I can take out 3, 6, 9, and 12. 4 goes into there, I believe, 55 times, and 5 goes into there 44 times. 7 will not work. Neither will 8. By the way, since 7 didn't work, I can take out 14. 8 will not work. You just divide it into, and you'll see it does not, but 10 does. 10 will equal 10 times 22, and then 11 times 20, and then 13 does not go into it. So these are all the factors for 220. Let me put that over here. Now I'm also going to do the same thing with 284. 284 is roughly equal to 16. And now let's go ahead and test each of these numbers. 1 goes into there 284 times. 2 goes into there 142 times. Now what about 3? If I take 2 plus 8, that's 10, plus 4 more is 14, and 3 does not go into 14. So I can take out 3, 6, 9, 12, and 15. Does 4? 4 does divide into 84. So I know 4 will go into the number. Let's check it out. 284, I think it's times 71 to be honest. Yeah, 4 times 71. 5 is not going to go into it because the number does not end in a 5 or a 0. 7, I don't think is going to go into it. Let's try it. 284 divided by 7. Nope, does not go in there. So 284 does, or 7 does not go into 284. Therefore 16 does not. Oh, by the way, I forgot. Since 5 didn't work, neither will 10 or 15. Let's try 8. I don't think 8's going to work. So 284 divided by 8, and I get a decimal. So 8 doesn't work. I would take out 16 if I hadn't already. All right, let's try 11 next. 284 divided by 11. I get a decimal. So next I have to try 13, 14. Oh, by the way, since 7 didn't work, I could have wiped out 14. So really all I need to test finally is 13. Another decimal. So I know that 13 is not going to work. Check this out. Look at the factors, or actually probably let's call them divisors. The proper ones, in fact. So the proper divisors of 220, we have 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. Now let's look at the proper divisors of 284. There's a lot fewer of these. There's only a total of 6 of them. So 1, 2, 4, 71, and 142. Actually, only 5 of them. Now, watch what happens when I add up these digits up here. 1 plus 2 plus 4 plus 5 plus 10 plus 11 plus 20 plus 22 plus 44 plus 55 plus 110. I'll just add them up left to right. 1 plus 2 is 3, 7, 12, 22, 33, 53, 75, 119, 174, 284. Now look what these numbers add up to be. So as I go from left to right here, I've got 1 plus 2 is 3, plus 4 is 7, plus 71 is 78, plus 142 is 220. So interestingly enough, the sum of the proper divisors of 220 is 284, and the sum of the proper divisors of 284 is 220. 220 and 284 are called amicable or friendly numbers. So as a definition, two natural numbers are called amicable if each is the sum of the proper divisors of the other. Note, 220 and 284 are the smallest known amicable numbers. The next pair is 1184 and 1210. After that, $17,296 and $18,416. These numbers obviously are difficult to find as well. Next topic we have is Goldbach's conjecture. Whenever you see the word conjecture, that means that it hasn't been proven. It means that we think it's true, but nobody has been bright enough to come up with a proof that shows that it to be true for in general. Well, anyways, let me go ahead and write what it means for Goldbach's conjecture. Notice that 4 can be written as 2 plus 2, and 2 is a prime. Let me move up to 6. 6 can be written as 3 plus 3. 3 is a prime. Then 8. So the game here is to try to write each of these even numbers as the sum of two prime numbers. They don't necessarily have to be the same prime number. As long as it's two different prime numbers, that would be fine as well. So A could be 3 plus 5. 3 and 5 are prime. I can do 10. 10 equals 5 plus 5. 5 is prime. 12 equals 5 plus 7. 5 and 7 are prime. 14 equals 7 plus 7. 7, of course, is prime. 14 can equal 3 plus 11. 3 and 11 are prime. So the idea is this. Every even number can be written as the sum of two primes. That's conjecture. And once again, I will reiterate, conjecture means that it has not been proven to be true. Every even natural number can be written as the sum of two primes. And you can see sometimes the primes can be the same one or it can be different primes. Whatever. Just to show you a couple more examples, I'm going to go in the other direction here. We have 100 can equal 3 plus 97, and 3 and 97 are prime. 98 can equal 31 and 67. 31 and 67 are prime. In fact, they have tried running computers, and no matter how much they run the computers for, they have never been able to find an example where there's a contradiction to this conjecture. So it stands out there waiting to be proven by some genius. The next topic, twin primes. So here would be some examples of twin primes. 3 and 5, 5 and 7, 11 and 13, 17 and 19. And this list goes on and on and on. Two primes are twins if their difference is 2. So you can see over here, 5 minus 3 is 2, 7 minus 5 is 2, 13 minus 11 is 2, 19 minus 17 is 2. So they're just primes that are separated by 2. One more pair, 71 and 73. definition. Let P be a prime number. Define P with a pound sign after it as equal to 2 times 3 times 5 times 7 ... up till you get to this number P. So it's kind of like a factorial. Now, P pound plus 1 usually results in a prime number. But not always. So for example, let's take a look at 13 pound plus 1. So the 13 pound part, I'll have 2 times 3 times 5 times 7 times 11 times 13, and then I have my plus 1. Well, this equals 30,031. And it turns out that this can be factored as 59 times 509. But many times you'll get primes. In fact, many times P pound minus 1 and P pound plus 1 will be twin primes. For example, if I look at 5 pound plus 1, that equals 2 times 3 times 5 plus 1, which is 31. Now 5 pound minus 1 will equal 2 times 3 times 5 minus 1, and that will equal 29. Or we can try 7 pound plus 1, that's 2 times 3 times 5 times 7 plus 1, that equals 211. 7 pound minus 1 equals 2 times 3 times 5 times 7 minus 1, which is 209. Now the first case, this one is actually happens to be prime, but 209 is not prime. In fact, it equals 7 times 29 equals 209. So getting a pair of twin primes that way is not going to work. But try a few and see if you can generate several collections of prime twins. We are familiar, most all of us, even if we have never had the subject in school, with the Pythagorean theorem. So this is known as the Pythagorean theorem. And we have lots of numbers will satisfy these things. Like if I do 3 squared plus 4 squared, that's 9 plus 16, which equals 25. And we know that's equal to 5 squared. So 3, 4, and 5 work. 6 squared plus 8 squared equals 10 squared. That works. 5 squared plus 12 squared equals 13 squared. So all of this works. And in fact, there's a whole collection of numbers that work. They refer to them as Pythagorean triples if they happen to work. However, there are no natural number solutions to the equation a to the n plus b to the n equals c to the n for n greater than or equal to 3. So we know it works for 2. When n is 2, that's the Pythagorean theorem. This is Fermat's last theorem. Also by Fermat, this theorem: every odd prime can be written as a difference of two squares in only one way. So whatever you do, it's unique is all they're saying. So some examples of this: 11 equals 36 minus 25. And of course that's 6 squared minus 5 squared. So the other one we had a sum of squares. This one is a difference of squares. 17 equals 81 minus 64, which is 9 squared minus 8 squared. 23 equals 12 squared minus 11 squared.